So I'm going to share the screen. And you get this crazy question. This one you're looking at?
Uh, yes, that's one example. That would kind of be what it is. But if can you scroll down as well, sir?
Yeah.
Maybe it's another one. I just have to keep going, sir. Oh,
That's
that
it.
was it. That
Yeah.
was it for all of them.
That was only 5 questions on this little guy.
Oh, no, not the practice test one, sir. It was for the other one,
All right, hold on.
the extra
So
credit.
the chapter 6 concepts.
No, sir. For the 10 questions that were the um maybe it may have been the concepts one. Yes, sir. It was an unproctored extra credit. You said it said.
Yeah. All right, hold on. I'm going to share. Um, this guy.
Yes, sir. Number three.
All right. You're given an integral 0 to 4 f of x dx equals 2. Check all integrals that are possible to find. All right. Um, well, let's just kind of run down the list here and talk ourselves through it. Can you see my cursor when I move it?
Yeah.
Okay, I just want to make sure. I'm looking at selection A here. The bounds, the bounds on the original integral are 0 to 4. And so x is traveling between 0 and 4. Here you have 2x. That means you're actually speeding up x, so to speak. And in a sense, you're covering the same, and how to put this, I'm going to use some informal language here, but you're covering the interval in half the time. So to go from x from 0 to 4 is the same as going 2x from 0 to 2. Does that make sense? Because that's what you're doing when you do a substitution. You're actually fiddling with the bounds as well. And so this first one is findable. Okay, the second one here, unfortunately, no, it's not, because we have no idea what f is, so we can't just assume that half of it, sticking the 2 out in front, that 2 can just move out to the front. It really doesn't affect anything except double, but we don't know what 0 to 2 f of x is based on this. So really, this question is emphasizing the nature of substitution and how it affects the bounds. The same is true here. The 2x would actually, as just discussed, it would actually have the effect of shrinking the bounds by a factor of 2. Okay, now this is a very general case. We have no idea what the actual function is. Okay, we only know what we're given in the original. So um, in this case, we have no idea what happens from 4 to 8. So there's just simply no way to infer anything. And here, yes, you could find it because it's the same integral as above, just with the 2 out in front. So the answer would be 4. And I guess D would not be applicable. Since I've got this up, does anybody have any?
Just to go on that same question, like I understand how to find A, like when they were in the homework, even I can
Uh-huh.
do it algebraically, like with the like just find the integrals, but I'm having a hard time conceptually understanding thinking about transformations is what I'm wanting to think about it. Because
Right.
like finding the area under the curve from 0 to 4, you know that that area is 2. So when I see f of 2x, I'm thinking I'm horizontally compressing it by a scale factor of 2,
Correct.
which is vertically stretching it.
Not necessarily.
No, okay, that's where I'm having a hard time
Right.
conceptually.
Because again,
So
F, it just depends on the function. we only know that we're compressing the x-axis or the interval in the x-axis by a factor of 2. It doesn't necessarily smush it upwards, so to speak.
Okay. Okay,
And
yeah,
you
because
know,
like doing it with the numbers, I was fine doing that, but I'm trying to figure out, like I was trying to put it together with the graph, like horizontally
yeah.
compressing it by a scale factor of 2.
Well, you know what you could do is you could actually experiment. You know, you could come up with a function whose area is 2 from 0 to 4, and then just see what happens when you know, compress it by a factor of 2. It can vary depending on the function. I could give you an easy one, it'd just be a constant function. I guess it'd
Just
be,
a rectangle. Yeah.
yeah, a boring rectangle. So uh, I guess f of x would be, I guess I'd want it to be at 1/4. No, 0 to 4. I wanted the area of 2, so 1/2. Um, f of 2x won't actually change to 1/2. So, because there's no variable in it. So in other words, it's function dependent. There's really only a very little bit that we can infer from this other than this factor of 2 is compressing the x-axis by a factor of 2. But I want to make something very important here. When you're doing the u substitution and you're actually trading out nonlinear uh, expressions for u, then it gets really weird because now it's almost impossible to visualize. You're totally dependent on the mathematics aspect of it. When you get to math 267, we actually discuss this very thing when we talk about Jacobians. Because what you're doing when you do a u substitution, you are literally transforming the function into an equivalent in a different axis system, a UV system, if you will. So there's really very little we can infer other than just what the nature is of the bounds.
Thank you.
Sure. How are you guys doing with the integrals? You hate them yet?
with a passion.
Yeah.
Yeah, they keep you up at night.
All right. Well, you know what? You're pretty much done with them. Once you take this test, that's pretty much it for the big integrals.
I
But did you
wish.
want to see a few? Anybody have any want to
I
look?
have a quick question about one from the integrals practice test you put
Uh-huh.
up, just like the PDF. Number 17.
All right. Let me pull it up. I've got it. This guy, x over x plus 2.
Yeah. When I solve this problem, I just put +1 -1 in the numerator and then split it. Is
Yeah.
that applicable?
Yeah, that
Okay.
would actually work just dandy. Actually, it's actually x plus 2. I would put a plus 2 minus 2.
Oh, okay, yeah.
Yeah. Actually, that's a good idea. Let me go ahead. You know what? Let me go to my overhead camera and I'll quickly. Yeah, this is kind of a deceptively challenging one if because you can do a couple things. You can long divide the bottom into the top, or like you said, actually put a plus 2 minus 2 on the top, and then split it up as x plus 2 over x plus 2, which is of course 1. And then the other guy is just negative 2 over x plus 2 dx. And suddenly this is an easy one. That's just going to be x, and then this is going to be 2 ln x plus 2, and you're done. Did y'all see that?
Yeah, so what I did was I U sub and turn x into u minus 2 and then split the
That'll,
fraction u over u,
that'll
u
work too. If you let
over
u,
u.
u is x plus 2, so x is u minus 2. And then, of course, dx is du because they're linear. So x would be u minus 2 over u. And you have that. And actually, it works out to be the same. It's going to be 1 over 2 minus u. So when you integrate, you get u minus 2 ln u. But then you make the replacement.
Mm-hmm.
Now, there's going to be one slight difference here. There's an extra 2 in your answer. but that's a constant. That can just get blobbed in with the C. You get the same thing.
Okay, that was my question too, because I did it both ways. I long divided first, which is the
Uh-huh.
same as Nicole's doing x plus 2 minus 2. You
Yep.
get that same answer. But then I did the U substitution as well, and I was like, wait, these so that 2 just gets grouped with the constant
Yep.
affecting the C.
Yeah, in
But
fact,
both of
if you left it the way it would still be correct.
okay, that was where I was like, these look different, but it just will give you a different C value.
Yep.
Okay.
Yes,
So both would be
absolutely.
acceptable. Okay,
Yeah,
because I was like,
both are perfectly fine.
okay,
All right, great, great, great.
thank you.
Are there like, I know on the test there's going to be questions saying which is the best choice, like the best process to be doing a problem. Like what we just did, we did it multiple ways. So is that like how do you decide which one's
Yeah,
the best way?
I'll tell you, the questions that ask for that will be pretty obvious for one particular
Okay.
way. I understand there was actually one in the ed discussions where I worked it out using trig sub, but then I realized I didn't even realize it until I was done that I said, wait a minute, what if I try by parts? And it worked. So
Yeah.
sometimes you can do it more than one way. And
Yeah.
but no, I know what you're talking about. The questions are such that it'll be pretty obvious.
Okay. Thank you.
Sure. Um, Let me share. So 16 on 6-2. Give me a second to copy it down. See, this would be a good question, like what would be the best kind of uh, technique? Well, in this case, a trig. So, oops, actually, it's fourth power. All right, is this a good one for everybody? This one right here, number 16? Kind of it looks pretty typical.
Yeah.
All right, let's just tackle this one. All right, there you are. First of all, you got to remember, there's a lot of trig to remember. I actually forget a lot of my trig, but I always remember the basic Pythagorean identity. Sine squared plus cosine squared is 1. If you divide by cosine squared, you get tan squared plus 1 is secant squared. And then if you subtract the 1, you get tan squared, the secant squared minus 1. And what you're doing is you're looking here, and which of these three closely matches? It looks like it's going to be one of these, the bottom one. And you want to choose your x in such a way that it also handles that 2. So we'll say x, I need to, when I square it, I want a 2. So I'm going to use rad 2 secant theta. That'll be my substitution. And then immediately I'm going to take the derivative, which is going to be rad 2 secant theta tan theta d theta. Okay. I'll pause here for a moment. Does that make sense?
Mm-hmm.
All right. Now, there was a question in Infinity, like the balancing part. And I want to mention here, there's actually no balancing necessary because you're just going to do a straight up replacement. The balancing actually comes from the chain rule. When I did the derivative here, the chain rule is actually just a 1. So I don't need to worry about balancing. So what I'm going to do is I'm going to fit everything. First of all, I'm going to bring that negative 10 out, just in the way. The dx I'll put on top. That's rad to secant theta tan theta d theta. Okay, I'm going to take to the power of 4. So rad 2 to the 4th power is actually going to be 4. And that's going to be secant to the 4th theta. And then here with the radical, I'm going to have, well, I'll go ahead and show the step. And you get that. So it looks pretty intimidating right now, but it's going to clean up. First of all, I'll do the radical right now. It's actually just 2 secant
Theta.
theta, well, square theta, and then minus 2. Factor the 2 out. Secant squared minus 1, that's tan squared. And then when you take the radical of that, you get rad 2 tan theta. So I'll tell you what, I'll rewrite it because I think it's important to see the whole structure. There's a lot going on here, but it's going to clean up. This whole radical is just simply rad 2 tan theta. And then we got d theta. All right. And again, I'll pause. Y'all see what I did there, just the substitutions and cleaning it up a little bit. Let me know if you have any questions. Yeah, I think you can see this is going to clean up real nice. The rad 2's cancel, tans cancel. One of the secants takes out one of these guys. So you have -10. And actually, we'll bring the 4 out. Let's just put it outside. I'm not going to worry about that at the moment. And this is actually just 1 over secant cubed theta and then d theta. And then that's actually cos cubed.
Cosine.
Very good. Yep. And then when you get an odd power of cosine, oops, that shouldn't have done that. That's a negative. I'm going to borrow cosine. And then now I'll tell you what, let me write the intermediate step here. It's cosine theta and then cos squared theta. Well, cos squared theta is actually 1 minus sine squared theta d theta. That's by your Pythagorean identity. And then I'll distribute. And we're rocking and rolling here. Oops, let me try again. Hold on. And then, okay, so far so good. Again, pop in, I can't, when you raise your hand, I don't necessarily see it, so you just have to kind of verbally interrupt. Is everybody cool so far?
Yeah, I think the only thing I do different when I get to cosine and 1 sine, my U sub.
Well, it sounds like we're on the right track, I think. We're going to do, yeah, exactly. This is going to be a U sub right here. This guy can just integrate cleanly to sine. So that's just sine theta. This is going to be a quick U sub. U is sine, derivative is cosine. The minus sign is going to stay alive. So it's going to be 1/3 sine cubed
Yes.
theta, just like that. And we're good. That's the antiderivative in terms of theta. Okay. And then now we got to convert that back into x's. So we go to the original way up top here. Let's bring that guy down. Let's put it over here. Draw yourself a generic right triangle. Let's see. We have that secant theta is x over rad 2. That means the cosine theta is the reciprocal of that. So that means x rad 2, and this will be 2 minus x squared radical. Did you all catch that?
Yes, sir.
All righty.
I actually have a quick question about
Uh-huh.
the previous step you were on. For the cosine and then sine, does it matter what you make the u substitution if like on the bottom part where you yeah, I can't see it because I'm talking, but like yeah, that part where you're at right now, if I made u sine and then du cosine or whatever, does it matter what you do with that?
Uh, yeah, it does. I mean, the only good choice would be u as sine.
Okay, yeah.
Because if you do u as cosine, then du is negative sine, but you have that square to deal with.
Oh, yeah.
Unfortunately, that messes you up. Now, sometimes you just get cosine sine, in which case you can pick either.
Okay. Thank you.
Cool. All right, so let's finish this off. So we look at our triangle. We look at so the sine of theta is going to be opposite over hypotenuse. So it's going to be rad 2 minus x squared all over x. So we just do some substitutions. I'm just keeping the -5 out in front. And then here, you know what? I'm going to be lazy and I'm just going to pop it into the cube. And I ain't going to worry about it. It looks good to me. What do you guys think?
Yes, sir. Look good to me.
I'll tell you what, hey, you know what? If you want to take an image, here's the top part. If you want to take a quick screen grab of that, I admit it's a tiny bit blurry. And then in a couple seconds here, I'll scroll it. So 3, 2, 1. There's the bottom part.
What are the odds we'll be allowed like a little cheat sheet with formulas, or that just like a no-go?
Nah, you gotta go with what's upstairs.
Yes.
The good news is that this is pretty much it in regards to nasty integrals. Have you guys looked ahead at all in the contents?
No, my brain's already a little
Nah,
overloaded.
yeah, I've been getting my
Okay.
butt kicked with these integrals.
Well, you're going to find that there's going to be a big shift in what we're going to be doing. We're going to be spending a lot of time, for example, on sequences and series. That's a whole different ball of wax. It's cool stuff. Um, and, we're going to also later on, I forget the ordering, but we're also going to be doing parameterization and polar curves and stuff like that. So there's a big shift in the approach here. If you can just gut through this stuff, then you basically are done with the big integrals pretty much forever. When you get to 267, which I teach, we don't ever do trig subs. In fact, in 267, the fanciest integrals we get are maybe some by parts ones. Um, but what you're getting here is you're really driving home a lot of the knowledge you need just to be good at this. You really need to be on top of your trig, you need to be on top of your algebra, and it's all the little stuff. So this is just really, really, really good practice in just coalescing this all together. All right, that was a lot of
I
fun.
did have a question then
Uh,
around the integration by tables. Is that
yes,
I know there was one of the sections that was covered, and a lot of that is refer to your formula sheets. Are those formulas going to be, if we do
yeah,
problems with that, are they going to be included within the question or?
it'll be included within the question.
Okay, thank you.
You will have access to Desmos. You'll have access to both the regular grapher, the Desmos / calculator, and then
And
you're
the
going to have
matrix.
and the matrix. And I encourage you guys, especially on those big partial fraction ones, don't waste your time spending like 20 minutes working out a 4x4 system. Just do it as a matrix. And there's a discussion on Ed Discussions where I show how to do that. So this is number 6 on that sheet. All right, so this is parfrac. It's been factored for you. This x plus 4 is a linear factor. So we're gonna just break it apart here. The linear factor gets just a constant in the numerator. This is an irreducible quadratic. It gets a linear numerator, just like that. Bring them back together into a common denominator. So the a is going to get multiplied by the x squared plus 5. And the x plus 4 is going to get multiplied by the bx plus c. Now, this is where we start. Let's go ahead and distribute this out. In fact, at this point, I'm just going to look at the tops only. Okay, the top here is x minus 2. The top here, if I distribute out, I get ax squared plus 5a. And then here I have to FOIL, I get bx squared plus 4bx plus cx plus 4c. And then I'm going to do one more quick reordering here. I'm going to order by powers of x. So I have ax squared and bx squared. So that's going to be a plus b. My x's, I have these two guys right here. 4b plus c. And then for my constants, I just have 5a and 4c. And again, I'll pause. And any questions how I got to there?
No.
Okay. This is where you start getting into the matrix, so a system. So if you compare left side and right side here, we don't have an x squared term over here. So This is going to be 0. We have for our x, we have a 1 in front of this x on the left, so that 4b plus c is 1. And then here, 5a plus 4c is -2. And that is a system. So what I'm going to do is I'm going to write that as a system. I'm going to write it where I kind of stack the coefficients and the constants. Okay. I've deliberately left some blanks there because I can treat this as like a 0C, and this would be a 0A, and this would be a 0B. Okay. And the reason for that is that I come over here, I'm going to create myself a matrix. And it's going to be, I just cut off coefficients 1, 1, 0, 0, 0, 4, 1, 1, 5, 0, 4, -2. Make that look like 4. There you go. Okay, so now what I'm going to do is I'm actually going to go to my Desmos. Give me a second here to bring it up. I'm going to go to desmos.com matrix, and I'm going to share it with you. So I'm going to create a new matrix, and it's going to be a 3 rows by 4 columns. And then I'm going to enter in the values, which was 1, 1, 0, 0, 0, whoops, 4, 1, 1, 5, 0, 4, -2. Where's my negative? Just like that. Enter it. And then the beautiful thing right here is you do RREFA, and bah, your answer's there. What you do is you click on this little icon, and it tells you what your A, B, and C are. You just read them off. A is -2/7. B is 2/7. C is -1/7. You all catch that?
Mm-hmm.
That's a big time saver.
Man, time.
I encourage you to use it. I have no beefs with that. As far as I'm concerned, I don't care how you solve your systems, just as long as you get it right. So I'm gonna
Professor.
Yeah.
So I was on the ed discussion. I recommended the use of that, and I appreciate you opening that up because is honor lock gonna block that as a root because
you'll have access to it. I've opened up both of those. You're gonna have access to both calculator and matrix.
Okay.
So
is it something we need to open up prior in a different web, or you open it up in HonorLock?
Just go in, close all tabs, go into HonorLock, start the test, and then you should. Honestly, I don't know what you see, but it'll come up. I've never had a problem with this before, so it'll pop up.
Yeah, there's on the right side of the screen, there's I think it's the third pull down menu. It says it's a links reference, and it should be right there for you.
So it'll be obvious. All right, I'll pause here. Is everybody cool so far with just the partial fraction going from here to here to here to here? All right, let's move along. So the integral becomes, all right, so here's what I do. I'm going to write integral, and what I'm going to do is I'm just going to cram that -2/7 on top. I'm not going to get fancy here. I'm actually going to split this up right now. I'm actually going to split it up as 2/7 x over x squared plus 5, take away 1/7 over x squared plus 5 dx. Okay, so I'm using the original parfrac form, and I've got my A, B, and C. This first one is just a natural log, so it's -2/7 ln x plus 4. This is just going to be a u du. Bottom is x squared plus 5. Du is 2x. So there's the 2x. That's going to be 1/7 ln x squared plus 5. And I always recommend on the UDUs, if you're not sure, just take a quick derivative of your answer and see if you get what you got there again. Now this guy right here is an arctan. The 1/7 is just a spectator. And the arctan formula is, well, that's your a squared. A squared is 5, so a is rad 5. It's 1 over rad 5 tan inverse x over rad 5. And that is good enough, plus c. You can bring these together if you want. You can rationalize. I don't really care. As long this is good enough.
Awesome.
All right. So any question? Okay, so I'll tell you what. Let me again, if you want to take an image of that. Um, I'm sorry, it's shaking a little bit. Then I'll scroll 3, 2, 1. You get that.
Professor, I also posted a link in our group chat here on Zoom with a link to how that is done on YouTube if anyone wants practice.
Yep. And I'm going to be posting this video um, after obviously after we're done. So it'll be alive there too, in case you miss it. All right. Well, that was a lot of fun too. Any other questions?
Oh, sorry, you go.
Go ahead.
Are there going to be any Riemann sums on the exam? Because I know that was 6.5.
Yes, the exam goes up through 6.5. So yes, you'll have to handle some of those with Riemann and midpoint, trapezoids.
Can you go over one example of Riemann sums?
Yeah, let me go. Let me go to Edfinity here. I'll bring up 6.5. You have a preference?
Probably right or left, either one
Okay.
or both.
Let's do this one, number 2, because this is the kind of the one you do like right and left. Okay. If you were just given points. If you were given a function like you are here on number 1, then you can kind of do midpoint. It's easy actually to locate midpoints. Simpsons, you can do that obviously. But number 2 would be the kind where you'd probably want to use left and right. Okay, so a radar gun is you. Let me share. Sorry about that. I forget. You got to tell me. So number 2 right here is a good one where we'd want to use left and right. A radar gun is used to record the speed of a runner during the first 5 seconds of a race. See below. Use Simpson's rule to estimate the distance the runner covered during those 5 seconds. Actually, we'll just use all of those. So I'll just show you how to do this. Let me copy that. I actually like vertical columns. I don't know why that is. So 0.5, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5. And then we had 0, 3.2, 3.5, 5.7, 7.5, 8.5, 9.65, 10.15, and then 8.5. I think I skipped one. What did I do? 9.5. What the heck did I do? Oh, I forgot my 5. Ah, here we go. All right. Sorry about that. I was confusing myself. So we have A5, 9, 5, and 9. All right. I'll plot a couple of them just to kind of give you a picture. So 0 plots to 0. We'll call this 0.5 and 1 and 1.5 and so on. 0.5 plots to 3.2. So how about 1, 2, 3, 4, 5? 1 plots to 3.5. 1.5 plots to 5.7. So once they kind of get the idea going, then it just kind of carries through. So on left rectangles, you're drawing the rectangles in such a way that the upper left corner over each interval touches the point. Now, the interesting thing about this is that the left rectangle for the first interval is 0. Do you see that?
Yeah.
So if I were to do left rectangles, each has a base of 0.5, so I'll just factor that out. These are just rectangles, so it's base times height. And I'm going to start with 0, and I'm going to add all the values plus dot, 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 all the way up to this 10.95. Actually, right here, I'm going to stop the left because when I draw my last rectangle way over here at 4.5 to 5, it'll actually touch up here at the left endpoint, 10.95. Now this one happens to have the same value, so you kind of lose that distinction, but just to be careful, I'm only adding the left corner. So it's going to be the first, all of these up to, but not including the last one. Does everybody see that? I'll do it real quick. I'm just going to crunch out the numbers. I got my handy little calculator here. So 3.2 plus 3.5 plus 5.7 plus 7.5 plus 8.15 plus 9.65 plus 10.15 plus 10.85 plus 10.95 multiplied by 0.5, and I get 34.825. I guess this is in, I forget what this is in, meters. Feet. All right, so feet. For the right ones, actually a lot of the calculations been done. It's the same base, 0.5. And you actually don't add this will actually be the only one you don't add. So for the right ones, you add up all of these guys. Okay, and you can actually just take your calculation from here and just make an adjustment. In this case, I don't need to subtract anything because I had a 0 there. So when I add up all of these numbers from 3.2 to this 10.95, I get 80.6, but then I multiply by 0.5 and I get 40.3. So 40.3 feet. Okay, is that so far so good?
Yeah, that makes sense.
Okay, and then normally what you do is you average them because it just makes sense. You have a low and a high, so 34.825 plus 40.3 sum, then divide by 2, you get 37.5625. That's a pretty reasonable estimate of the runner's distance. For midpoint, we can't really do midpoint on this one because we don't actually have any midpoint values. We could, I suppose, cheat and just take the average, but you know what? We'd actually just end up repeating the work we just did. For trapezoid, let's do that one. It's always, so basically the area of a trapezoid is the base times 1/2 the left height plus the right height. So it's the average of the left and the right. And you know what, I'm looking at this one, we're actually going to just end up repeating the same value. So for example, for this one right here, it'd be first it'd be 0.5, and then the average is 0 and 3.2, so 3.2 over 2. For the second interval, it'll be 0.5, then the average of 3.2 and 3.5. And you just basically do that all the way to the end. For the third one, it'd be the average of 3.5 and 5.7. And you go all the way up to the end. For the last one, it would be the average of these last two, which is actually going to be 10.95. Now there are ways to shorten the load here. I mean, you can just pull out the 0.5 and you recognize that like 3.5 over 2 and 3.5 over 2 just make 3.5. So the arithmetic is not as daunting. Am I making any sense, or is this helping?
No, it makes sense.
Okay.
Thank you.
How you guys doing on this one? You want me to go on, or?
I just have a question about the Simpsons rule. I feel
Uh-huh.
like once I got there, I just got into survival mode of knowing how to do the Simpsons rule. But why are why is it the change of x over 3? And then that pattern of the 1, 4, 2, and like symmetric pattern. I guess I
That's
don't know what
actually
I'm
not,
doing. I'm just plugging it in.
it's actually not easily explained in a few moments. I can tell you that the Simpsons rule is actually parabolas. That you, instead of using trapezoids, you're actually using parabolas. And you're taking them 3 at a time. You know what? I'll tell you what. I hate to say this. If you just want to memorize Simpson's rule, that's sufficient. I have some stuff on Simpson's rule that I can maybe, well, I'll post it to like Canvas if you want to take a look at it. It's a little more theoretical. Would that be all right?
Yeah, that's fine. Like I said, I know how to do it. I just don't know what I'm doing or why, and I kind of want to know
Yeah,
that.
it's not the easiest thing to explain in a few moments. It's because what you're doing is you're taking points 3 at a time, the first, second, and third, and you're actually fitting a parabola to them. And then you take the second, third, and fourth, and you fit a parabola to them. And you end up actually adding each point 3 times, except for the first one and the last one. It gets a little funny. So again, I'm not doing a good job of explaining it just
Yeah, no,
verbally.
if you want to post it, like I don't need it for the test. I'm just
Yeah.
wanting to like make sure I know what I'm doing or why I'm doing it, but I know how to do it.
So Simpson's rule is I'll tell you what, I won't do the whole thing. You take the interval length 0.5 divided by 3, and you take the first endpoint, which in this case is 0. You take the last endpoint, which make sure you guys can see that. Yep, we take the last endpoint because I have to have the table handy too, which is 10.95. And then in between, you're actually going 4 and 2 and 4 and 2, and you always have to make sure you end up at a 4. So it has to alternate. And then you're doing the functional values, so 3.2, 3.5, 5.7, etc. And then you just punch that out in your calculator. Um,
Why did you? I know it has to be even. Why did you not include number 5, the last 5?
oh, I just ran out of space.
But if you use that 5, would that have made the number of entries odd?
How many do we have here? We have 11. Yeah, you're right. I guess it worked out. All I know is you know what? Actually, you're right. I misspoke. You always have to have a 4-2-4 in the middle. So it always has to be 4-2-4 or 4-2-4-2-4. You always have to start and end on a 4, which means you're going to have an odd number of terms. And then the first and the last will make it odd. So my bad. I apologize. A little math humor for you. Don't. guys watch The Simpsons at all? All right. I'll tell you what, I'll post something online for you guys just to show you some of the theory. All right. Well, we got time for maybe one more. Anybody want to pose one?
Professor, sorry, I just want to clarify. You said every question on the test will be from the homeworks on the Edfinity, right? So a good way to review would just be making sure I know how to do every problem on the
Pretty
homeworks.
much, yeah. And
All right.
also do those two practice ones, the honor lock practice and the chapter 6 concepts.
Got it.
Because I'm just trying, and then also do that thing that I sent you, that PDF.
Yeah.
Yeah, I'm just basically just trying to throw as much as I can at you, and just so you guys can get practice. Because really, that's what it boils down to, is just practice. There's
Okay,
no
got it.
shortcut to these, as you've discovered. But again, the good news is once you've gotten through this, you can kiss this stuff goodbye. It's in your rearview mirror. All right. So yeah, you have a whole bunch of questions like on use substitution, and then
I
you have.
Oh yeah, sorry.
Go ahead. No, go ahead, please.
Was looking over my notes again, and one of the things from early on that I guess hasn't quite made it through to today is the usage of the boomerang rule,
The what rule?
or I guess the use. And this is from one of the lectures, but I think it was in use substitution. Let me go back through my notes real quick.
Oh, when you do an extra substitution on top of that?
I'm
not familiar with the term boomerang rule.
Yeah, I guess that's one of the. I guess yeah. If someone can help me out here.
Yeah.
So yeah, the boomerang was in it's almost like you're just doing a repeat. It's like an iteration.
Okay.
Like you just kind of repeat.
When you set it equal to
reducing.
I. Set it
Yeah.
equal to I. And then it appears again.
Oh, are you talking integration by parts?
Yeah, and it's like an e to the 5x sign, and then it circles back to sign, and you set it equal to.
I'll tell you what, let's do that one. I know what you're talking about now.
Okay.
I just never heard the term boomerang rule.
Yeah, it was one of the ones mentioned in the lecture. So
Yeah. Oh, you know what? I want to show you something too. So we'll do this one pretty quick. We do u equals e to the 5x, and then dv is sine x. And then we'll take the derivative. Du is 5 e to the 5x. And v is going to be, you integrate to get negative cos x. So you start piecing together your uv, so you have negative e to the 5x cos x minus v du's. The minuses will make a plus integral. Bring the 5 out, e to the 5x cos x. All right, so far so good. And now you have to do it again. U is e to the 5x. This time dv is cos x. du is 5 e to the 5x. V is going to be sine x. It gets a little messy, so I'll tell you what, just kind of follow the equal sign. This guy comes down. We have negative e to the 5x cos x plus 5. And then I do these two together, so I get e to the 5x sine x minus the integral. It's going to be a 5 e to the 5x sine x dx. And this is where you get that self-referencing. It actually references the original integral. Okay. I think that's what they're talking about. So if I clean this up a bit, let's distribute that 5 through. It's going to make a 25. Suddenly you've got the same integral twice. Well, actually, you have this guy on the left, and you have 25 of them on the right. So we're going to bring this guy to the right. We're going to actually add this whole thing to the right side, to the left side. So I have 26 of them, e to the 5x sine x. Nothing has changed here. And then one last step, you just divide out by the 26 and you are all done. That's what they were referring to, correct?
That appears to be, yeah. Thank you.
I have
All
a
right.
question about this.
Uh-huh.
You can't use tabular method with this specific
No, you can't. I was
integral.
actually going to show you tabular because that's another question that came up that I think, I don't know if they cover it in the videos, but
They do.
okay,
Yeah.
the tabular is a beautiful, let me just do an example of tabular. If you did like x to the 4th, e to the 3x dx, if you do integration by parts, you're going to have like 4 or 5 nested cases. So what you do is you make 2 columns, differentiate and integrate. You just keep on differentiating until you get to 0. Oops. And then on the other side, you just integrate each time. And then you just draw diagonals like this. You alternate signs. And then you just piece them together. So the first one's going to be x to the 4th times 1/3. So you have 1/3, x to the 4th, e to the 5x. And this is going to be negative 4x, 4/9, x cubed, e to the, I'm sorry, 3x, 3x. And then here you have 12 and 27, so plus 12 27ths, x squared, e to the 3x, minus 24 over 81. I don't know if that reduces. Yeah, it does. 8 over, it doesn't matter. I'll just continue down here. It's going to be minus 24 over 81, x e to the 3x. And the last guy is going to be plus 24 over 243, e to the 3x. And I don't really care if you don't reduce. When you start getting big fractions, that's okay. Infinity is pretty um, good at accepting equivalent forms. So if you don't reduce like 24 over 81, no big deal. But this is a good shortcut for doing nested tabulations.
And then, sorry, I was just wondering why wouldn't this method work for the first problem?
Because you need to end up at 0.
Okay.
If you try it with this one, you just keep running in loops. So yeah, it won't work on this one. Tabular only works if one of the factors is a polynomial because you can drive it down to 0.
Get it down to 0. Okay.
All right. Well, I'm going to wrap the show up. It is 7 p.m. where I live. Thank you for joining. We had a really good crowd. So I'm going to end this. I'm going to have, it's going to take a while for the video to load. So I'll send an email or an announcement out to everybody. I'm going to be gone for the first part of tomorrow morning, but I'll be back in the early afternoon, and hopefully that there won't be any big fires. I think everything's set up good to go. Good luck to everybody on the test. At some point during this upcoming week, I'll circulate grades. Now the grades do dump into Canvas, but they can sometimes be misleading. So I'll circulate some grades that are a little more accurate, so you know what your status is. That'll probably be more toward the end of the week. All right.
Thank
All
you.
right. Cheers.